Today I'm going over image production. These are factors that affect radiographic quality. How this chart works, all these factors are going to increase, and I will go over which ones affect receptor exposure. Remember, receptor exposure is the amount of radiation reaching the image receptor. The first one is mass. Think of quantity, those number of X-ray photons. So if we increase our mass, we are definitely increasing receptor exposure. If mass doubles, receptor exposure also doubles. It has a direct relationship. Next one is kVp, kilovoltage peak. Think of quality, penetrating ability of the beam. So if I increase kVp, receptor exposure definitely increases. It has a direct relationship, but they are not directly proportional. So what does that mean? So think of the 15% rule. If I increase my kVp by 15%, receptor exposure doubles. So that is not in proportion, right? We're going up kVp by 15%, receptor exposure is going to double. So that is why it is a direct relationship, but it is not directly proportional. Next is OID, which is object to image receptor distance. That is basically from the body part to the image receptor, and that has no relationship with receptor exposure. Next is SID, source to image receptor distance, source from the X-ray tube to the image receptor. So for example, let's say we are going from 40 to 72 inch SID. That is definitely going to decrease receptor exposure. Think of the inverse square law. If I am increasing that distance, there is less intensity. I'd like to think of the campfire method. So if I'm close to the campfire, intensity is going to increase, right? Because I'm literally close to the campfire. If I increase my distance, go farther away from the campfire, intensity decreases. Next is large and small focal spot size that has no effect on receptor exposure. Next is tube filtration. So that filter removes those long wavelength photons and also reduces patient dose. So if we are removing long wavelength photons, receptor exposure definitely decreases. Next, we have grids. So for example, going from a 12:1 to 16:1 grid ratio, that is definitely going to decrease receptor exposure. Why? Because in a 16:1, there's going to be more lead content in that grid, so less radiation is going to go through. So receptor exposure goes down. The amount of radiation reaching the image receptor goes down. Next, we have beam restriction. That is collimation, right? I like to think of making that square smaller, tighter. So that is going to decrease receptor exposure. There's going to be less radiation reaching the image receptor because that square is smaller. It's tighter. Next, we have the anode Hill effect. So there is more intensity on the cathode end than on the anode end. So it's both. So since there is more intensity on the cathode end, our receptor exposure increases. On the anode end, since there is less intensity, receptor exposure decreases. Motion, no effect on receptor exposure. Now let's talk about patient factors. So I like to think of imaging a sthenic patient to a hypersthenic patient. That is the average body type, the sthenic. 50% of the population have this body type. And then we have the hypersthenic patient. That is going to be a massive, stocky, larger build. 5% of the population have that body type. So whenever we are imaging a patient that is larger, that is definitely going to decrease receptor exposure. Why? Because most of that radiation is going to be absorbed by the patient because they are larger. They have more adipose tissue, so less is going to go through, most is going to get absorbed. So that is why the amount of radiation reaching the image receptor goes down. Next, we have patient factors, so pathology. So we have additive and destructive pathology. So additive, for example, Packett's disease, that is going to require an increase in our exposure factors. So that is going to decrease receptor exposure. Why? Because more of that radiation is going to get absorbed and not go through the patient and reach the image receptor. So receptor exposure goes down. Now it's going to be opposite for a destructive pathology like RA, for example. We need to decrease our technical factors so receptor exposure goes up because more radiation is going to go through the patient and reach the image receptor. Next, we have angling to part or receptor, and that has no effect on our receptor exposure. Next, I'm going to talk about spatial resolution. So think of sharpness, good detail on our image. And again, increasing all these factors, I'll let you know which ones affect spatial resolution. Mass KVP do not. OID, SID definitely. So talking about OID, so if we increase that distance, we increase that object to image receptor distance, spatial resolution goes down, detail on the image goes down. Why? Because of size distortion, because of magnification. The body part becomes magnified. So we always want the body part close to the image receptor as much as possible to decrease that magnification. Next is SID. So going from 40 to 72, that is going to increase spatial resolution, direct relationship. So if that distance goes up, spatial resolution goes up as well. Next, we have focal spot size. We have a large and a small. Small focal spot size, so imaging smaller body parts. That is going to increase detail on our image, but a con, less heat dissipation. Large focal spot size, imaging larger body parts. That is going to decrease detail on our image, but a pro, better heat dissipation. Filter, grids, collimation, anode heel effect have no effect on spatial resolution. Next is motion. So if your patient happens to move during the exposure, that is going to decrease spatial resolution. Your image is going to come out blurry, so you'll definitely have to repeat that. Patient factors, size, imaging the average body type to the massive stocky build. That is going to decrease our spatial resolution. So think of imaging, an obese patient. Our detail on our image is going to go down. Our image is going to come out very foggy as well because of that scatter radiation reaching the image receptor. Patient factors, pathology, no effect. Angling the tube part and receptor. That is going to decrease detail on our image when we do that. But sometimes we need to angle our tube. Next, we have distortion, and we have size and shape distortion. Size is magnification. Shape, we have two categories that fall under that. That is going to be elongation and foreshortening. Mass KVP, no effect on distortion. OID, SID, definitely. So if we increase that OID distance, magnification goes up. Magnification goes up, guys. So again, we want the body part as close to the image receptor as much as possible to decrease magnification. Next, we have a SID going from 40 to 72. That is going to decrease our magnification on our image. So for example, whenever we take an x-ray of the lateral C-spine, there is OID there. So that is why we increase our distance to 72, right, to compensate for that OID. Focal spot size, filter, grids, collimation, anode heel effect, no effect, and motion, no effect. Now, when it comes to our patient factors, our size again, so sthenic patient versus the hypersthenic patient, that is definitely going to increase size distortion, increase magnification. Because again, imaging an average size patient to an obese patient, for example, that is going to magnify everything because that patient has a lot of tissue. Factors have no effect. Pathology. Now let's talk about our angle. Whenever we angle the tube part or the receptor, the IR, that is definitely going to increase distortion. So we have shape and we have size distortion. So I talked about size already. So shape distortion, guys, elongation and foreshortening fall under that. So for elongation, what causes that is misalignment of our CR tube and our image receptor. For shortening, that is going to be misalignment of the anatomy. But sometimes, guys, we do want elongation on our image. So for example, let's say we are imaging for the scaphoid, ulnar deviation, for example. We want the scaphoid to be elongated, so we need an angle. So sometimes we do need that for good reason.